Since the dawn of human navigation, the Earth's magnetic field has been our silent guide, an invisible force generated deep within the planet's molten core. But for decades, a radical question has haunted the halls of theoretical physics. Could this field be more than just a compass guide? Could it be a source of limitless, clean energy? Today, we are standing on the precipice of a new era. A team of international scientists has just published results from a landmark experiment that successfully converted the Earth's magnetic flux into usable electric power. This is not merely a laboratory curiosity. It is a fundamental shift in how we perceive the resources of our planet. For the first time, we are moving beyond burning fuels or capturing sunlight to directly tapping into the kinetic energy of the Earth's rotation and its internal dynamo. This deep dive will explore how we reach this point, the staggering physics that makes it possible, and why this discovery might just be the most important technological milestone of the 21st century. We begin by looking at the planet not as a rock, but as a massive, rotating electrical generator that has been spinning for billions of years, waiting for us to finally plug in. To understand how we can extract power from the Earth, we must first understand the engine that creates it. Deep beneath our feet, the outer core, a sea of molten iron and nickel, is in constant, violent motion. This motion is driven by convection currents and the Coriolis effect caused by the Earth's rotation. This process, known as the geodynamo, creates a massive magnetic field that extends thousands of kilometers into space. This field is not static. It is a dynamic, pulsating web of energy. The experiment in question focuses on the principle of electromagnetic induction. According to Faraday's law, a change in magnetic flux through a circuit induces an electromotive force. On a planetary scale, the Earth is effectively the magnet, and our atmosphere is the medium. The challenge has always been the sheer scale required to capture a field that, while massive, is relatively low in density at the surface. By understanding the fluid dynamics of the core, researchers have identified specific hotspots where the magnetic flux is most concentrated, providing the ideal locations for the first generation of planetary power harvesters to begin their work. The breakthrough didn't happen in a vacuum. It required the perfection of high-temperature superconductors. In a secret facility located in the high deserts, researchers constructed a device known as the flux-cutting array. This system utilizes a series of ultra-conductive tethers suspended by high-altitude platforms, reaching into the ionosphere, where the magnetic field is less distorted by terrestrial interference. As these tethers move through the Earth's magnetic field lines at orbital speeds, they experience a constant change in flux. The result is a steady, measurable flow of electrons. Previous attempts at this technology, such as the tethered satellite experiments of the 1990s, were plagued by material failures and the inability to manage the massive voltages generated. However, using new carbon nanotube composite wiring and advanced power regulation systems, the current team has managed to stabilize the output. They aren't just creating a spark, they are generating kilowatts of power from nothing but the motion of the planet itself. This hardware represents the culmination of 30 years of material science research, proving that we can finally build structures strong and conductive enough to withstand the stresses of planetary energy harvesting. The scale of the energy available is truly staggering. Calculations suggest that the Earth's magnetic field contains enough energy to power human civilization for millions of years without any perceptible impact on the planet's rotation or the field's protective qualities. The beauty of this system is its consistency. Unlike solar power, which depends on the day-night cycle and weather, or wind power, which is intermittent, the Earth's magnetic field is a 24-hour-a-day, 365-day-a-year resource. The experiment demonstrated that by placing these harvesters in strategic locations, we can create a global grid that is entirely independent of traditional fuel sources. During the peak of the experiment, the team observed a phenomenon where the harvested energy increased during solar storms, essentially turning the threat of solar flares into an opportunity for massive power surges. This resilience makes the technology a perfect candidate for a primary global energy source. We are looking at a future where energy is not something we manufacture by burning or splitting atoms, but something we simply collect from the environment we inhabit.
Of course, a discovery of this magnitude brings significant skepticism. Critics have long argued that the energy density of the Earth's magnetic field is too low to be practical. However, the data from the recent breakthrough tells a different story. By using a multi-layered resonance technique, the researchers were able to amplify the induced current significantly. They discovered that by vibrating the conductive tethers at specific frequencies that harmonize with the Earth's natural magnetic oscillations, known as Schumann resonances, they could increase the efficiency of power extraction by over 400%. This was the eureka moment. It wasn't just about moving through the field, it was about moving in rhythm with it. This resonance-based harvesting means that the physical size of the collectors can be reduced, making them more cost-effective and easier to deploy. The oscilloscope readings confirmed a stable, high-frequency AC output that was easily converted for use in standard electrical grids. The data proves that we have moved past the theoretical phase into the realm of viable engineering. One of the most profound aspects of this technology is its geographical flexibility. Because the magnetic field is everywhere, energy can be harvested anywhere on the globe, though it is particularly potent near the poles where the field lines are most concentrated. This has enormous implications for remote regions that currently rely on expensive, dirty diesel generators. Imagine research stations in the Arctic or remote villages in the Himalayas having access to an infinite supply of clean energy simply by deploying a small magnetic harvester. Furthermore, the experiment confirmed that the process of energy extraction actually has a stabilizing effect on the local ionospheric conditions, potentially offering a way to mitigate some of the electrical disruptions caused by solar activity. We are seeing the birth of a technology that doesn't just provide power, it integrates with the planet's natural systems. The environmental impact is virtually zero, as there are no emissions, no radioactive waste, and no consumption of finite resources. It is the ultimate expression of living off the land, but on a subatomic and planetary scale. As we look toward the future, the integration of magnetic power could lead to the realization of Nikola Tesla's greatest dream, the wireless transmission of power. Because the Earth's magnetic field is a global medium, it could theoretically be used as a carrier for energy distribution. The researchers are already looking into coupled resonance systems that could allow energy harvested at the poles to be transmitted through the magnetic field itself to receivers located anywhere on Earth. This would eliminate the need for thousands of miles of copper wiring and high-voltage transmission lines, drastically reducing the cost of infrastructure. A world powered by the magnetosphere would be a world of total energy abundance. This abundance could fuel the next industrial revolution, making processes like large-scale desalination, carbon capture, and space exploration significantly cheaper and more accessible. We are talking about a fundamental change in the economics of human civilization, where the cost of energy no longer dictates the limit of our ambitions. The road ahead is not without its challenges. Scaling this experiment from a successful prototype to a global utility will require unprecedented international cooperation and massive investment. There are also regulatory and geopolitical questions to answer. Who owns the rights to the Earth's magnetic energy? How do we ensure equitable access for all nations? But the hard part, the physics, has been solved. We now know, beyond a shadow of a doubt, that the planet we call home is a literal powerhouse. The breakthrough experiment has given us the key to a door that has been locked for a century. As we move forward, we must do so with the realization that our relationship with the Earth is changing. We are no longer just inhabitants of a planet. We are the operators of its most profound natural engine. The success of this experiment marks the end of the era of scarcity and the beginning of the era of planetary energy. The Earth is ready to power our future. The only question left is how fast we are willing to build it.